And welcome back to another exciting lesson. I know 9.3 was a little bit longer to get through. I'll go and tell you settle in because 9.4 is the same way. We're learning that reflections, and we'll see in this lesson, rotations, just take a little bit more of our thought process, a little bit more thinking, a little bit more understanding. So in this lesson, without further ado, we're learning about rotations. So let's take a look. We'll look at our learning targets as always. We will perform rotations on and off the coordinate plane, just like we've been doing with the translation, just like we did with the reflection. We're going to perform rotations on and off the coordinate plane, as well as identify and distinguish between reflectional and rotational symmetry. We saw reflectional in the previous lesson, dealing with lines of reflection. And now we're going to see something called rotational symmetry. Makes sense? We're studying rotations. So I probably forgot at the very beginning of the lesson, but as always, rank your understanding as you read this text. You might know a little bit about rotations, so give yourself a 2. Or if you know nothing about rotations, maybe give yourself... Sorry about that interruption, but if you would rank your understanding, if you have no idea, maybe put a 0 or a 1. It says, for the big finish of the Marching Cougars performance, this is our last rigid motion, Mr. Scott arranges the band in a triangle formation again. Then the triangle appears to rotate clockwise around a point like a pinwheel. The center of the rotation is the vertex located at 0, 0, also known as the origin on the coordinate plane. If you would, go ahead and draw a line at the bottom of your page. Read through the text, especially look at the math terms here, highlight some important things as you go before playing through the video. Okay, hopefully you're playing through now, you've taken a second to really try to digest this information, and there really is a ton to process here, just like with the reflections. But hopefully you notice that this triangle here, it definitely appears to be turning. We see that it's pointing down here, then it's pointing left, then it's pointing up, and we could safely assume if we kept going, it'd be pointing right, and then back down as the rotations continue. So it says the spinning type of transformation is called a rotation. It is defined by 2 very important parts, the center of the rotation and the angle of the rotation. We're going to see here how this differs from a translation and a reflection where there's a lot more moving parts. In fact, we have a center of rotation, tells us what it moves around. And I love that it pointed out here, the center of rotation actually doesn't move at all. Things move around it, just like you can picture the Earth moving around the sun. We move around the sun, and the sun is the center of our solar system. So the center of rotation maps to itself, and we use the angle of rotation to tell us how many degrees and in what direction to actually rotate our figure. They let us know that the center of rotation may be part of the figure being rotated, as we see up here. 0, 0 is our center of rotation, and notice it maps to itself, not just because it is in fact the origin and it's 0, 0, but because it is the center of rotation. There are several functions we're going to look at, a lot to uncover here. Several of the major functions that we're going to look at are clockwise 90 degrees, 180 degrees, and 270 clockwise. And I also love that they pointed out counterclockwise here. So I'm using these 2 words, clockwise and counter, and I'm realizing some of you might not know what I'm referring to. So let's, in fact, look at a clock. So you see here, I've essentially drawn the X and Y axis, but using a clock for reference. So if we start at the X-axis here, start at 3 o'clock, 90 degrees counterclockwise is actually the opposite the direction that our clock hands travel. That's why we call it, that's in fact why we call it counterclockwise. So counterclockwise is the opposite direction that the clock hands actually travel. So this would be 90 degrees counterclockwise. That's the notation you'll see me use, CCW. And if we started at 3 o'clock and went 90 degrees clockwise, we'd end up at 6. This is known as 90 degrees clockwise. And you'll see that notation. Now, if you notice in the text, we actually didn't have to specify 180 degrees clockwise or counter, because if we go 180 degrees, we'll end up at 9 o'clock, regardless of which direction we go. So we don't actually have to specify which direction we're going, clockwise or counter, when we speak about 180 degrees. The last thing I want to look at is how 90 degrees clockwise and 90 degrees counterclockwise actually imply our last degree, 270. So if I start at 3 o'clock and I travel 270 degrees clockwise, can you guess what number I'm going to end up at? So if I start at 3 o'clock and travel 270 degrees clockwise, I'm going to end up at 12 o'clock. Well, if you notice, if I start at 3 o'clock and went 90 degrees counterclockwise, I'll also end up at 12 o'clock. So we'll see that the function for 90 degrees counterclockwise is the same function for 270 clockwise, because you end up in the same location. That's all transformations are really trying to discuss, is where they end up after the transformation. So if they end up in the same location, it's the same function. Well, likewise, if we go back to 3 o'clock, I'll try to use a different color here. Go back to 3 o'clock and we travel 270 counterclockwise, we're going to end up at 6 o'clock. 270 degrees counterclockwise, we end up at 6 o'clock, which was the same as traveling 90 degrees clockwise. So 90 degrees clockwise, that function is the same as the 270 degree counterclockwise. And the reason that's nice for us is that it doesn't double up how many functions we have to memorize, because 90 degrees counter and 270 clock are the exact same function. So picture a clock, if you need to, as we really start to uncover and look at all these functions in the book. So let's go back to our book. So the first column was the 90 degrees clockwise function, and it tells us two things to do. We're going to swap our x and y. Notice a coordinate is typically written x and y, or it's always written x and y. And then the function tells us to swap those two values around. So if I was at 310, then I'm going to be at 10.3. Well, notice not only did we swap them around, but we made our x's negative. So the 90 degrees clockwise function tells us to do two things. Swap x and y, and also change the sign of our x. So 310 went to 10, -3. And -310, when you swap 10 and -3, the 3 then becomes positive. Then showing you there that, yes, if it's already negative, you change it to positive. This really means, when we see that negative in front of x, it really means change the sign. Notice I said that earlier. We're changing the sign of x. Notice 0, 0, the center of rotation, or the origin, did not change. So that's how you perform a 90 degrees clockwise rotation, is you swap x and y, change the sign of x. Swap x and y, change the sign of x. This second column here that tells us every point goes to -x, -y, we simply swap the signs of both x and y. So we had our pre-image 310, so our image will be at -3, -10. And if our pre-image was located at -310, the -3 becomes +3, and the 10 becomes -10. We change the sign. And like we see here again, 0, 0 does not change, not because it's just 0, 0, but because it's the center of rotation. So before we just blow through these functions, because they're just written for us, I'd like to take a second to really explain how to interpret and how to understand these functions a little bit better. So when we're talking about rotations, we see these three main functions here, the one for the 90 degrees clockwise, 180 degrees, and 270 clockwise. And so the first function we need to learn is the 90 degrees clockwise function. We kind of looked at what that looks like on a physical clock and where the image will end up. So the function tells us to do two things. Every point will go to, the y and x will swap, and then we'll change the sign of the x, right? So the y and x will swap, and then we'll change the sign of the x. Well, if we go back to our clock, when we start thinking about 90 degrees clockwise as it relates to 180 degrees, the book actually tells us this, but if we travel 90 degrees counterclockwise, or 90 degrees clock, I believe we're talking about clockwise here. So if we travel 90 degrees clockwise and then travel 90 degrees more, we have traveled 180 degrees. And then if we travel 90 degrees more, we travel 270 degrees. And then if we travel 90 degrees more, we end up right back where we started, 360 degrees. So we can actually use this function to help us understand what the other functions look like. So let's go back and take a look. So this function tells us to swap y and x and change the sign of x. So the 180 degrees function, think about it. If it was like this, swap y and x, so y and x will end up back where they were, and change the sign of the second number, which now we have the function for 180 degrees. So if you swap y then x, change the sign of the second number, then we have the function for 180 degrees. Likewise, with 270 clockwise, take the 180 degree rotation function, swap y then x, so you'll have negative y, then negative x, and then change the sign of the second number. And that's what the 270 clockwise function looks like. Just the sign of the y is changed. Now recall that 90 degrees clockwise and 270 counter are the same, and 270 clockwise and 90 degree counter are the same. So these are the three major functions we study when we deal with rotations. Now, hopefully you're asking yourself, why don't we study 360 degrees clockwise or counter? Because you end up in the same location. 360 degrees clockwise or counter, every point would go to or map to itself. So hopefully with these functions a little bit more understood and a greater sense of what clockwise and counterclockwise means, let's take a look at our next item, 2 through 3. So if you would, take a second and draw a line below 3 right above 4 and complete items 2 and 3 before continuing with the video. So hopefully you took a second to predict the direction of the arrow after these rotations. The center of each rotation is 0, 0. That's important. I actually highlighted that here with the green. So after a 90 degrees clockwise rotation, hopefully you think if this is pointing at 12 like it is, then it'll be pointing at 3 on a clock, which would be pointing to the right. And if we went back to our pre-image and went 180 degrees, it would point down at the 6 o'clock. And then if we went 90 degrees counterclockwise or 270 clockwise, it would actually point left or at the 9 o'clock position on a clock. So it said draw these 3 rotations, and were your predictions correct? Yes. I wanted to point out something here, pun intended. If you're wondering how I was able to handle this, of course you can use the functions on the previous page, but if you're understanding the functions a little bit better, or just rotations in general, the distance from any point to the center of rotation is preserved. So I knew, let's say for instance that this point was 2 units or 1 square away from the center of rotation, it had to remain that same distance after I rotated 90 degrees clockwise. And then, for example, the tip of the arrow was located at 0, 10. So after the rotation, it would need to end up at 10, 0, and it would rotate 90 degrees clockwise, and it would stay still 10 units from the center of rotation. And then we go 180 degrees, right? And we're pointing down. Notice we didn't have to specify clockwise or counter. And we went also 90 degrees counterclockwise, which is the same as 270 clock. I just want to remind you here that those 2 directions are one and the same, or not necessarily the same direction, but they end up in the same location. But this is a really important point, pun intended, to highlight here that the distance from any point to the center of rotation is preserved. Just like we saw with reflections. Any point, however far it was from the line of reflection, that's how far the image point was after the reflection. We're seeing a lot of similarities there. So now let's press on to item 4. Recall that we're learning how these rotations affect figures. We're learning specific distances, in this case, directions. We're learning what the center of rotation does and how important it really is. So let's move on to item 4. It says, describe the rotation that maps figure A onto figure B. And it gave you a hint. First, identify the center of rotation. So I actually want 2 things here. I want to know the center of rotation for each of these. And when it says to describe the rotation, we need the direction, which is counter or clockwise, as well as the degree of rotation, 90, 180, 270, and so forth. So make sure you give me all those things when describing the rotation here. And I'll show you, after you play through the video, I'll show you exactly what I'm looking for and how it should be written. So hopefully you took a second to figure this out. I do want to point out one thing. It says, describe the rotation that maps figure A onto figure B. And for a second, just ask yourself, why is it important that they tell us that figure A maps onto figure B and not vice versa? Well, hopefully you're figuring it out that if we started with figure B and then mapped to A, these directions would actually be reversed. If we map from figure B onto A, that would actually be a 90-degree counterclockwise rotation or a 270 clockwise. So it's very important that we pay attention to the wording here that tells us that the figure maps from figure A onto figure B. That really stresses the direction. So this is a rotation 90 degrees clockwise or 270 counter. I use the arrows here to help you, about the point 10. When we talk about rotation, and specifically the center rotation, we say that it rotates about the point or around the point. In this case, the center of rotation was 10. If you're wondering how I figured that out, it's because I noticed a point on rectangle A did not move when it mapped onto rectangle B. And it was this point located at this vertice of the rectangle. Recall that center of rotations do not move. They map to themselves after rotation. So that's how I figured out that this, in fact, was the center of rotation. And if you're wondering how I knew it was 90 degrees clockwise, well, this point here at this vertice of the rectangle maps here. And one of the cool ways is if you connect corresponding points to the center of rotation, as I'm doing now, connect corresponding points to the center of rotation, you can actually see the angle that's formed by these 2 segments. In fact, it forms a 90-degree angle. Or if you look at the other direction, it's a 270-degree angle. So that's what you can do to help you figure out the degree of rotation and use corresponding points to find out the direction. This second one down here was probably a little bit tougher, but if you notice, none of the points on figure A remained in the same location to map to figure B. So we knew the center of rotation had to be off of the figure itself. And if you notice these little blue dots here, the way I figured it out was points, however far a point is from the center of rotation, that's how far it has to be after the rotation. So this point on triangle A corresponds to this point on triangle B. So I knew that the center of rotation had to be somewhere in this region so that it would be equidistant. Those corresponding points would be equidistant from the center of rotation. So I figured it out that it was, in fact, located at 1, -2. And notice I said here that it could be 2 locations or 2 directions. We can describe it by 2 directions. We could say 270 degrees clockwise or 90 degrees counterclockwise. So I said a rotation 270 degrees clockwise or 90 degrees counterclockwise about the point 1, -2. Well, what I like to always do right here is take a second and teach you how to rotate points or how to rotate figures when the center of rotation is not the origin. The book really just readily assumes that you're comfortable with that. Notice you didn't actually have to perform the rotation here. You were just supposed to figure out what it was. So I'm going to hop onto another screen here to show you how to rotate figures around center of rotations that aren't necessarily the origin like we see here on item A and B. So if you need an extra sheet of graph paper, go and get that out now as we look at rotating figures around points other than the origin. So this math can get a little bit tricky, so pay special attention, watch and rewatch as needed to understand what's happening here. So take a second, pause the video. You can draw and write down all this information on a separate sheet of graph paper as needed. But I have triangle X, Y, Z here. I have my center of rotation located at 5, 1. And we are asked to rotate triangle XYZ 90 degrees clockwise about the point 5, 1. Now, this is the function that we use for a 90 degrees clockwise rotation. It tells us every point will go to, we'll swap X and Y and change the sign of the second number, or in this case, when we swap it, we'll change the sign of X. Now, that function is only useful, or its main use, when we're rotating figures around the origin. In fact, most of the functions we see for rotations are rotations around the origin. But there has to be a way that we can still rotate this triangle XYZ around a point other than the origin, or in this case, 5, 1. So to use this function again, what we're really doing is we're rotating the figure around the origin. So the math that we're going to do, if I can explain, is we are going to take this triangle and this center, and we are literally going to shift it left 5, down 1, so that the center is quote unquote around the origin. And then we're going to rotate it using the function as it's written, and then translate where it is and the center back to 5, 1. Now you'll actually see the rotation after we perform it and actually after we draw it. But that's the math that we're going to be doing here. We're shifting it left 5, down 1. We're moving everything back to the origin so we can use this function as it's written. So the way we do that is we're going to take each point, and the first thing we're going to do, if you're a step follower, is we're going to subtract the center of rotation. By subtracting the center of rotation, in this case it's located at 5, 1, by subtracting 5, we're going to move everything left 5, and if we subtract 1, move everything down 1, moving it to the center, or to the origin. Once we have subtracted the center of rotation, then we're going to apply the function, because the function is written to be used when the center of rotation is the origin. So once we have kind of quote unquote translated it to the origin, we'll use the function, and then we will add the center of rotation back. We'll add that coordinate back. So then what we're really doing by adding 5 and adding 1 is we will essentially move back right 5 and up 1. And that's how we are going to perform rotations when the center of rotation is not the origin. So for example, if you're following along, X is located at 1, 2, 3, 2. So to find X prime, the first thing we're going to do is we're going to subtract the center of rotation. Subtract the coordinate 5, 1. Now hopefully you know 3 and 5s are X's in coordinates, so we're going to subtract those two numbers. 3 take away 5 is -2. And 2 take away 1 is 1. And at this point, we have subtracted the center of rotation. So let me show you where that point is. -2, 1. Excuse me, that's -2, 2. -2, 1 is here. So think about it. We just shifted point X 5 to the left and 1 down. That's what we just did. We're shifting this entire triangle, in fact. Now we're going to... Actually, I think I did 4. Looks like I did 4. Let me do one more. Yeah, one more. So I shifted it 5 to the left and 1 down. And so notice, I like to point this out, pun intended. Look how far X is from the center of rotation. And we're making our new center of rotation, the origin. Look how far it is here. So we're really just mapping it around the origin so we can apply the function. So now to apply the function, you swap X and Y. So 1 will go here, -2 will go here. Then you change the sign of the second number. So it'd be 1, 2. So we have just rotated that point this point here to 1, 2, which would be here. So there's that 90-degree rotation, right? There's that 90-degree rotation. And then because our center of rotation was not the origin, the last thing we need to do is actually add the center of rotation back. So we're going to add 5, 1. And our final point, our image for x prime, will be located at 6, 3. So I'll graph that point here. So 6, 3 is here. So there's where x is going to be. Now, again, if you connect corresponding points to the center of rotation, you should see the degree of rotation. And of course, we see that here. There's that 90-degree rotation that we were expecting. In fact, 90 degrees clockwise. So let's finish it out with the math for y and z. So I'm running out of room on that end over there, so I'll do y over here. Y is located at 2, 3, 4, 5, 2, 5. So again, we will subtract the center of rotation. 2 take away 5 is -3. 5 take away 1 is 4. We will apply the function, which again tells us to swap x and y. So swap x and y, then change the sign of the second number. Then we will add the function, or excuse me, the center of rotation back. So we'll add 5, 1 and find that y prime is located at 9, 4. So let's go graph that. Here's 5, 6, 7, 8, 9, 1, 2, 3, 4. Now, if you can't tell already, it looks like our triangle is now pointing to the left. Now, you could finish out z if you want the practice, but you know that a rotation preserves the size and shape of a figure. So if y is 2 units from z, then y prime, excuse me, I forgot to put my primes, y prime has to remain 2 units from z prime. So without actually doing the math, I can locate where z prime will be. But if you'd like me to, just for a little bit more practice, I'll show you how to find z prime. Again, take the image point z, or excuse me, the pre-image point z, which is located at 4, should be 4, 5. Subtract the center of rotation. So we're going to subtract the point 5, 1. 4 take away 5 is -1. 5 take away 1 is 4. And so again, what we're really doing here is we're shifting this left 5 and down 1. So let me show that. So be located at -1, 4, 1, 2, 3, 4. So this is where quote unquote z is after we have subtracted the center of rotation. So look how far z is from the center of rotation. Now look how far it is if we're assuming the center of rotation is the origin here. Now let's add apply the function, excuse me. So the function tells us to swap our x and y. So we'll swap x and y, change the sign of the second number. So -1 will become +1. So this is us rotating this point here. It's rotating this point 90 degrees clockwise, which will be located at 4, 1. Which will be located here. And then we have to shift it back by adding the center of rotation 5, 1, which would be adding 5 to the right and up 1, which we see that's where z prime was supposed to be. So we'll add 5, 1, and z prime will be located at 9, 2, which we assumed because a rotation is a rigid motion, so the size and shape is preserved after the rotation. So if you are realizing that this math here that you see for x, y, and z prime, if you see that that math is a little bit tricky to you, let me know. I will also post another video to hopefully help you with that math. So let's return to the text now and see what else rotations has for us. So we've done an extensive deal studying rotations on the coordinate plane. And so let's just take it a little bit step further. So now we're really focusing on the angle of rotation. We've been referring to it as 90 degrees clockwise, 180 degrees, 270 degrees, and so forth. The angle of rotation can be used to describe the image of every point of the figure. Consider the rotation shown below. Rectangle ABCO, that's this rectangle here, is rotated 90 degrees clockwise, so we see that, 90 degrees clockwise, and maps onto rectangle A prime, B prime, C prime, and O. And can you might guess the main reason why O did not move? Well, O is the center of rotation, or in this case, the origin. From the diagram, it appears that AO is actually perpendicular to A prime O, and that CO is perpendicular to C prime O, and so forth. And BO is perpendicular to B prime O. So if this is true, if you measure angle BOB prime, you will find that it too equals 90 degrees. This is what we were suggesting on that previous diagram, that if we connect a point or connect corresponding points to the center of rotation, we actually connect those points to form an angle, we see the angle of rotation that we've been using. So if you connect, and I'll say that again, if you connect corresponding points to the center of rotation, you can actually observe the angle of rotation. So with that in mind, the following figure is a square that is centered around the origin 0, and point A is one vertex of the square. If you would, go and draw a line at the bottom of your page and answer items 5 and 6 using this concept in mind, how we can connect corresponding points to the center of rotation to then observe the angle of rotation. So pause the video, try to complete 5 and 6 before playing through. Okay, so we were actually asked to draw a rotation of the square 45 degrees clockwise, and that is important here because it tells us specifically where A will map to. Clockwise about the origin, and label the point A prime that is the image of point A. So I wrote this note over here, pretty basic. 45 degrees is half of 90 degrees. So we've really been just studying 90-degree increments, 90, 180, 270, 360. And so this book took the opportunity to kind of explain what happened when it was half of 90 degrees. So what I did with this red here was I connected A to the center of rotation, which is the origin. And then I suggested with these dots that this is actually the 90-degree rotation. So A would actually map to this vertex if it was a 90-degree rotation. Well, if it's half of that, if 45 degrees is half of 90, then A will actually, when I connect it to the origin, half is right here. So that's how I knew where A prime was going to end up, by using this concept of angle of rotation. So again, if I connected A to O to this vertex, it was 90 degrees. So if I knew if I took half of that, I would find the location of A prime. Well, it is a square, so all of these points would be in similar locations on the X and Y axis because they are all the same length. Now, they didn't necessarily give us any of the other vertices, so we didn't necessarily have to label anything here. Item 6 then asks, what is the measure of angle AOA prime? And I really want to stress why they're asking that. They're asking you to find the angle of rotation. And the way you find the angle of rotation is you connect corresponding points to the center of rotation to form an angle. Again, A and A prime are called corresponding points. And in this case, O is our center of rotation. And when we connect A, O, and A prime, we form an angle. In this case, it's 45 degrees. So we can find the angle of rotation by connecting corresponding points to the center of rotation. That's really what they're trying to stress there. What we're going to do now is we're going to really take the concepts that we're learning about rotation and pull them off the coordinate plane and notice some characteristics, some key characteristics that again will apply on the coordinate plane as well. So we're going to use geometry software again. So we're going to use Geogebra here to explore rotations. First, use the software to draw a quadrilateral. That's a four-sided figure. Not necessarily, in this case, a square, rectangle, trapezoid, rhombus, none of those, but just a four-sided figure. Then plot a point P that will serve as the center of rotation. Use the software to rotate the quadrilateral 120 degrees counterclockwise around point P. So I'm going to show you how to do that with GeoGebra. So let's hop over to GeoGebra now. Notice I've already drawn a very similar quadrilateral as the one, and I've also plotted the point P that will serve as our center of rotation. So I believe the directions told us to rotate this quadrilateral 120 degrees counterclockwise around point P. So you can take a second, pause the video if you need to, draw your polygon, use the polygon tool to draw one, and then use the point tool to draw point P. It honestly doesn't matter the size of your polygon, if it looks just like the one in the book, or where your center of rotation is, as long as your center of rotation is not on the figure itself. Hopefully you can start suggesting that that would infer something different. So we're going to find the transform section. We are going to rotate. Notice that even GeoGebra kind of helps you understand what's happening here. We translate using a directed line segment, also known as a vector. You reflect across or about a line, but you rotate around the point, or a point, in this case, P, the center of rotation. So it tells us to select our figure, then select the center of rotation, and notice this little screen pops up, and they give us the choice to do 120, 45, whatever degree we want to rotate, as well as counter or clockwise. I believe the default is counterclockwise, which they have asked us to do here, but you can always change that as needed. So we're going to rotate 120 degrees about or around point P as directed. And after we rotate it, we see that it goes ahead and labels all of our image points with a little apostrophe representing prime. So now that we have this done, let's see if we can go back to our text to see what things we need to discover through GeoGebra. So let's take a look. So it says choose a point of the pre-image and there's that word, corresponding point of the image, and use the software to measure the distance of each point from the point P. What do you find? Then it asks us on item 9 to use the software to measure the angle formed by a point, its image, and point P with point P as the vertex of the angle. So we're using corresponding points and the center of rotation to find the angle. And it says, what do you notice about this measure? Then they ask us on item 10 to use the software to change the shape of the quadrilateral by dragging one or more of the points that form the quadrilateral. Do the results from item 8 and 9 remain true no matter the shape of the quadrilateral explained? So we have a little work to do. First thing, we're going to choose a point from the pre-image and its corresponding point and find the distance from those points to the center. So let's go back to GeoGebra. We're going to find our measuring tool, so distance or length. And I actually found out that you don't have to draw a segment between points and the center of rotation. I don't believe you have to find the distance. So we'll start with point F to P. And it tells us the distance of FP. Didn't even realize that, FP. The distance from F to P is 2.1, and the distance from F prime to P is also 2.1. We can do that again if you'd like, just so you can see that it's not just those 2 points. Maybe let's do point D to P is 3.6. So D prime to P should also be 3.6. So if you would, take a second, go back and answer to item 8, what happens to the distance of corresponding points in the pre-image and image in relation to the center of rotation? So I said that both points, and the book said same distant, but I wanted to keep using this term here, equidistant. So both points are equidistant from P, or in this case, the center of rotation. So a point and its corresponding point from the image and pre-image should remain the same distance from the center of rotation. So then item 9, recall what it said, use the software to measure the angle formed by a point, its image, and the center of rotation. So let's go take a look at that. So we are to find the angle between corresponding points in the center of rotation. So again, I don't actually think we have to draw the angle itself. We just select those 3 points. So to measure an angle, we'll do F, P, and F prime. And if you notice, it's a little bit hard to see here, but behind that P is a 1. So an angle formed by a point, the center of rotation, and its image is actually the same degree of rotation that we perform the rotation with, or the angle of rotation. And we can do that with several other points if you like, just to make sure. So we'll do these further points, D, P, and its corresponding point, P prime, and we see, or D prime, excuse me, we see that same angle of rotation. So let's go back and answer our text. What do you notice about this measure? Well, it's 120 degrees, or same as the angle of rotation. So again, we can find the angle of rotation, or use a point and its corresponding point in the image to find the angle of rotation. Lastly, on 10, and this is where you can play around a little bit, you are tasked with changing the points of the quadrilateral to see if what we said in items 8 and 9 still remains true. So let's hop over to GeoGebra. I am going to go ahead and get back some of those distances we saw before. So we'll see from D to P, or we'll do another point actually. Let's say from C to P and from C prime to P as well. So they are asking us to drag this quadrilateral bit. So I'll specifically move C, which will then alter C prime naturally, and see if a lot of the characteristics we saw in item 8 and 9 are still true. Is the rotation still 120 degrees? Well, we see that the distance from C to P and C prime to P is going to correspond. Those distances remain the same. And if I drag D, no matter how I drag D, you see that angle changing, but not necessarily the degree. It's just changing along with where those points are now on this plane here. So yes, these things are remaining the same regardless of what the quadrilateral looks like. Even if I were to drag point D way out here, and we can maybe zoom back a little bit, it's still suggesting that the angle of rotation is still 120 degrees. And the distance from any point to the center of rotation remains the same. So we can kind of play around with this as much as we want. And we see what we learned in items 8 and 9 still remaining true. So now let's continue our exploration off the coordinate plane. We see like translations and reflections, rotations can also be defined independently or without the coordinate plane. A rotation that maps any point to its image, so in this case P to P prime and Q to Q prime, has the following properties. Let O be the center of rotation. So we're learning some things on the coordinate plane and off the coordinate plane such that these two properties are in fact true. So let's take a look at a couple of these properties that we're really trying to hit home. So this says the distance from P to O is equal to the distance from P prime to O. So that's what we're seeing with these rotations. However far P, one point, is from the center of rotation, its image after the rotation is the same distance. They are equidistant from the center of rotation. And likewise with Q and Q prime. Forgot to mark that as prime. And with the angle of rotation, we're seeing something very important here, that the angle of these two corresponding points and the center of rotation should be equivalent for any corresponding points. So the measure of angle POP prime, which looks like a 90-degree angle, from Q to the center of rotation to Q prime should also be a 90-degree angle. So those are the two key properties we're trying to draw from these rotations. Now, to describe rotations, we will use the following notation, just like we saw with translations and reflections. There is a notation. So let me explain what a couple of these key components are. Pun intended. In fact, the capital R stands for reflection. The first subscript letter next to it, subscript is when it's written on the bottom, like a submarine. The first subscript letter is O. This is our center of rotation. what follows after the comma, m degrees, is the angle of rotation. So those are the two key components. So we're saying that any point when it undergoes a rotation about the point O using this degree or this angle of rotation, we get the result P prime. So again, P prime, the image, is the result of rotating point P this many degrees, m degrees, are the measure of the angle of rotation around the point O. So number 11, which we're going to do a little bit differently, we're not going to necessarily do it in our book, I've actually put it on Geogebra as well. It says the diagram shows isosceles triangle. Remember, an isosceles triangle has two congruent sides. In this case, we could really suggest that line segment AB and line segment BC are congruent, and point O inside it. It says draw the following rotations and label the images of the three vertices. Well, they just throw you through a loop here because they start using these rotations, and in fact, they start using these negative degree rotations. If you notice, none of A, B, or C are in fact using 270 degrees or 180, but they are introducing this negative 90 degree rotation. So let's speak on that. So with the initial discussion of rotations, we used a clock to help us. So let me write these numbers here. And we said if we started at the 3 o'clock and rotated 90 degrees clockwise, we'd end up at 6 o'clock. Or if we rotated 90 degrees counterclockwise, we'd end up at 12 o'clock. Well, if you can't tell, this clock really suggests the X and Y axis, where 3 and 9 run through the X axis and 12 and 6 run through the Y axis. Now, referring to positive or negative degrees instead of clockwise or counter, when we see an angle open up from the x-axis, or if we had a ray here and it opened up, that is a positive degree. And if we have an angle that opens, let's use a different color. If we have an angle that opens down, we have a negative degree. So what we're really suggesting here, and it's a little backwards to our thinking, is that counterclockwise is a positive degree, and clockwise, which is what we're used to, is in fact a negative degree. So maybe I should put a little equal sign there so you don't confuse the two. So when it says rotate around the center O, negative 90 degrees, we're actually rotating 90 degrees clockwise. Now you probably ask yourself, why don't they just say that? Well, we're learning some new notation. That's the point here. We're learning new things. And on B, when it says rotate around point C, 90 degrees, positive 90 degrees, we're actually suggesting 90 degrees counterclockwise. So the last one, item C, rotate around point A 90 degrees, we're saying 90 degrees counterclockwise again. Now, every year at this lesson, I love to take just a second to kind of explain why we're seeing some of the things in mathematics. And hopefully you find some interest to what I'm about to tell you. So when we created this idea of mathematics, we didn't just discover it by digging up a textbook. In fact, the people that created mathematics as we know it actually observed the world around them. And so a lot of the things we see in mathematics are based upon the world around us. Specifically, when we talk about rotations and the coordinate plane, let's think about the x and y axis, or the coordinate plane, if you will. So if you didn't know this, this section up here is known as the first quadrant. Everything is in fact positive in the first quadrant. All x's, all y's are positive. And despite what you might think, it doesn't go left, right, top, bottom. It actually goes the other direction. We start in the top right quadrant, which is the first quadrant, and then we move left, and this is our second quadrant. And in the second quadrant, our x's are negative and our y's are positive because we went left on the x-axis and up on the y-axis. And then we keep moving in a circular fashion. And our third quadrant is down here where everything is in fact negative, x's and y's. And then last, our fourth quadrant is over here where we have positive x's and negative y's. So you probably are asking yourself, why does it start in the top right and work its way counterclockwise? Well, what direction does the sun rise in the morning? Well, if you didn't know this, the sun actually rises in the east, which is over here on the x-axis, and then follows this path, right? Or at least I believe the sun's not actually rising, we're actually rotating. But in that same idea, the sun actually travels in a counterclockwise motion. Well, then you might be asking yourself, well, why does our clock go the other direction? Well, if you've ever done a sundial before, a sundial uses a stick in the middle of a circle, and you actually use the shadow to point to the time. Well, the shadow is moving the opposite direction of the sun. So as the sun travels counterclockwise, the shadow moves clockwise. That's why we actually use the term clockwise and counterclockwise. So for us to suggest that a counterclockwise rotation is in fact positive, while a clockwise rotation is in fact negative, is based on when they first discovered what mathematics was by observing the world around them. So that's why the quadrants are actually listed 1, 2, 3, 4. And why when we refer to positive degrees, we're talking about a counterclockwise motion. And when we say negative degrees, we're talking about a clockwise motion. Just to give you a little fun fact into the history of why we do some of the things that we do in mathematics. So now let's pop on over to Geogebra, where I've drawn a very similar figure, and we're going to rotate this triangle ABC using these three directions. So our first direction tells us to rotate triangle ABC about point O, negative 90 degrees. So remember, O is going to be our center of rotation, and negative 90 degrees actually means a clockwise rotation. So let's find our rotation about a point. Here we go. So we're going to rotate about a point. So the first thing we're going to do is going to select the object, select the center of rotation, which is point O in this case, and then it tells us 45 degrees counterclockwise or clockwise. We are, of course, going to do a 90 degrees clockwise, or a negative 90 degrees rotation. So there we have it. It looks like it, in fact, rotated around that center point O. And notice it labeled it A prime, B prime, C prime. Then the next directions tell us to rotate around point C, I believe a positive 90 degrees. So that's, in fact, a counterclockwise rotation. So we're going to do another rotation around a point. So I'm going to select my object, select my center of rotation, and then we are going to do a positive 90 degrees, which is in fact 90 degrees counterclockwise. And we see what happens there. Now they've actually labeled it as C prime 1, A prime 1, B prime 1. More often than not, we'll actually see that written as A prime prime, B prime prime, C prime prime. So I'm actually going to pause the video and change that real quick. So now that that's fixed, hopefully you see now A prime prime, B prime prime, and C prime prime. It's easy for us just to kind of quickly go through these rotations, but recall what they're really trying to stress for you here to understand and appreciate some of the characteristics of these rotations. In fact, on the second rotation, they told us we'd rotate around the point C. Well, notice you can't actually see point C anymore because C prime prime is in that same location. Remember, the center of rotation maps to itself. A couple things, don't forget, you can always explore the angle of rotation. We can go up and measure an angle. So we choose corresponding points and the center of rotation. So for our second rotation, we could say from A to the center C to the its corresponding point, A prime prime, and you notice that a little box is already being drawn there, suggesting it was, in fact, a 90-degree rotation. So don't forget some of the tools that you can actually use that we've already learned as we've discovered more and more about these rotations. So now let's perform our last rotation, which I believe is a rotation 90 degrees, positive 90 degrees. So it'd be 90 degrees counterclockwise around point A. So like we saw in the last one, we are rotating around a point on the original figure or the pre-image. So A prime prime should not go anywhere, right? Points that are the center of rotation, if they're on the figure, they're going to map to itself. So I'm going to go ahead and find our rotation tool. So we're going to rotate this pre-image, triangle ABC, around our center A. And we're going to do a positive 90 degrees, or in this case, 90 degrees counterclockwise. And again, they suggest that it's B prime 1. So I'm going to go and change that real quick by pausing the video. So if you are following along on GeoGebra, hopefully your rotations look a lot like what you see here. And again, don't forget to go back and explore some of the characteristics we're seeing by measuring some things. Hopefully you notice that, yes, the size and shape of all these figures is in fact preserved because a rotation is a rigid motion. So just keep that in mind as we explore GeoGebra. You really can't mess anything up. If you ever feel the need to, you can hit this back arrow to undo anything you've done. But use GeoGebra to explore and have some fun with it. You can even alter, if you'd like to, alter your pre-image shape and notice how it moves those corresponding points so that it still holds true to all the rotations we just did. So have a little fun with it as we move back into our lesson. So let's continue on. It says, item 12, describe 3 rotations that each map a square onto itself. So take a second, see if you can figure it out. They are wanting you to use this type of notation here. So keep that in mind when you're talking about rotations at this point, because we're not necessarily using the coordinate plane counter or clockwise. So what I came up with, very similar to the book, rotation of 90 degrees. In this case, that is counterclockwise, rotation 180 degrees, and a rotation of negative 90 degrees, which is clockwise, where O is the center of the square. So I wanted to show what that looked like on GeoGebra because GeoGebra is off the coordinate plane, or we don't have a coordinate plane. And all I did was draw these lines to find the center of the square, which I labeled O. And I wanted you to see what happens when I rotate this square about this point O with those 90 degree intervals, starting with 90 degrees. So I'm going to select my square, select my center O, and start with 90 degrees clockwise, or excuse me, counterclockwise. And watch what happens. In fact, it looks like nothing shows up, but if you can see very clearly when I undo, it got a little bit darker. That's because they drew the shape perfectly on top of where it was. In fact, it said map to itself. And so I can repeat that process again by rotating around a point, clicking on that new image around the point, and we could do 180 degrees. And we could do clockwise or counter because 180 degrees counter or clockwise is the same location. And then we see it get darker again. But nothing has really, in a sense, moved because it's mapping it onto itself. And we'll do that one more time with 270 degrees. So I'll rotate, click on my square, my center of rotation, and we'll do 270 degrees or 90 degrees clockwise. And we see that it just gets darker still. So what we're seeing here is this idea of rotational symmetry, how we could rotate this square about the center of the square so that it appears to not move, or what the book says, maps onto itself. So let's use that idea as we press on to item 13. So it says, review your answer to item 12. Figures such as squares have what's called rotational symmetry, meaning that a rotation of less than 360 degrees can map the shape onto itself. In other words, suggesting that it doesn't move. So we could rotate any of these figures, assuming they have rotational symmetry, of less than 360 degrees, because if we rotate it 360 degrees, of course it's going to end up back where it began. That's what 360 degrees does. So anything less than that, if it appears to map exactly where it was, then we say that it has rotational symmetry. And the smallest such angle that we could rotate it so that it appears to map to itself is known as the angle of rotational symmetry. So if you would, draw a line at the bottom of the page and then complete. Sorry, my pen wasn't working for a second. Complete item 13 before playing through the video. So I wanted to start this off a little bit different. If you notice, all I did was draw the lines of symmetry, highlighted a very important piece of information here. But I found this really cool way that if we can visualize reflectional symmetry, and we learned that in lesson 9-3, if we can visualize reflectional symmetry, I found a really cool way, a simple way to then determine if it has rotational symmetry. So 13 told us to identify if it has rotational symmetry, reflectional symmetry, or both, and that's suggesting that it could have one or the other. And it says also identify the angles of rotational symmetry and lines of reflectional symmetry. And remember, the angle of rotational symmetry is the smallest such angle that it can be rotated so that it maps onto itself. So we've already looked at an isosceles triangle, which tells us that these two sides are congruent. Those two sides of an isosceles triangle are in fact congruent. So there has to be at least one line of symmetry here right down the middle. And so it does have reflectional symmetry, but does it have rotational symmetry? So I found this really simple way to determine if a shape has rotational symmetry. I honestly don't know if this formula or concept exists. It probably does, because I'm probably not smart enough to think of these things on my own. But I realized if it has to be less than 360 degrees, if we take 360 degrees and divide by the number of lines of symmetry, this number here can actually tell us the angle of rotational symmetry. So in fact, we're seeing how reflectional symmetry and rotational symmetry go hand in hand. So for example, and you'll see how I use it a little bit uniquely on item A. Item A, we see that it only has one line of symmetry. So if I'm following this concept here loosely, I take 360, divide by 1, and we get 360 degrees. So does it have rotational symmetry? Well, if we go back to the definition of rotational symmetry, it has to have a rotation of less than 360 degrees that can map it onto itself. So by getting this answer, I am suggesting that no, in fact, an isosceles triangle does not have rotational symmetry. It does have one line of reflectional symmetry, but no rotational symmetry. So let's see how we can, again, apply this formula to item B. Item B is an equilateral triangle. We studied that back on lesson 9-3. So it has 3 lines of reflectional symmetry. So let's see if it has rotational symmetry. Well, hopefully you can suggest if you turn this triangle around this center point where all 3 of those lines of reflection intersect, that of course it would have rotational symmetry. But then to find the angle of rotational symmetry, we're going to use this formula idea here. So 360 degrees divided by 3, we get 120 degrees. So because this number is less than 360 degrees, we are suggesting it does in fact have rotational symmetry. So we'll say it has rotational symmetry. And they asked us if it does in fact have rotational symmetry, what is the angle of rotational symmetry? So in this case, 120 degrees is our angle of rotational symmetry. In other words, we could rotate this equilateral triangle 120 degrees around this center point, and it will appear to have not moved, or in this case, mapped onto itself. Now let's take a look at the rhombus. We saw the rhombus back, I believe, in lesson 7-2. The rhombus is a quadrilateral with all 4 sides congruent. And notice here, because all four sides are congruent, in fact, there are actually two lines of symmetry that we could draw. So the rhombus has two lines, or excuse me, of reflectional symmetry. So then we have to ask the question, does it have rotational symmetry? So using the formula, 360 divided by 2, we get 180 degrees. So since that number is less than 360, it does have rotational symmetry. And this degree we found here, that is the angle of rotational symmetry. So in other words, we could rotate this rhombus 180 degrees around this center here, where these two lines of reflection intersect, and it would map onto itself. The last one we're going to look at is known as a regular hexagon. I love how they squeeze this in here at the last second, trying to teach you what regular means. It doesn't mean it's not, or it's normal, and there's ones that aren't normal necessarily, but regular actually has a specific definition. And any regular polygon, each side of that polygon has the same measure, so we're suggesting all 6 sides of this polygon are congruent, and each angle has the same measure. And each angle, whatever degree that is, and we'll actually learn later on that all of those angle measures are in fact congruent. Well, if you're not picking up on it, there's a reason it needs to be a regular hexagon, because in order for a shape to have reflectional or rotational symmetry, sides and angles have to be congruent to one another. So it's actually very important that they tell us it is a regular hexagon. So this regular hexagon has 6 lines of symmetry. So hopefully you're figuring out it will, so I probably should say here, it has reflectional symmetry. So it will definitely have rotational symmetry. So we'll take 360 degrees, divide by 6, and we get 60 degrees. So yes, it has rotational symmetry. And 60 degrees is our angle of rotational symmetry. Goodness, tongue-tied. In other words, we could rotate this hexagon around this point 60 degrees and it would map onto itself. And that concludes the lesson together, lesson 9-4. Hopefully you got quite a bit out of it. I know it's a lot to extract. Hopefully you're getting the hang of GeoGebra. Be sure to watch any part of this video that you need to. Definitely brush up on this page, as a lot of you are probably still learning what reflectional and rotational symmetry is. And as always, go back to your learning targets and reevaluate your understanding after watching through the video. Thank you all for watching. Have a great day.